Fluid dynamics. The motion of a fluid is usually extremely complex. The study of a fluid at rest or in relative equilibrium was simplified by the absence of shear stress, but when a fluid flows over a solid surface or other boundary, whether stationary or moving, the velocity of the fluid in contact with the boundary must be the same that the boundary, and a velocity gradient is created at right angle to the boundary. The resulting change of velocity from layer to layer of fluid flowing parallel to the boundary give rise to shear stresses in fluid. Individual particles of fluid move as a result of the action of forces set up by differences of pressure of elevation. Their motion is controlled by the inertia and the effect of the shear stresses exerted by the surrounding fluid. The resulting motion is not easily analyzed mathematically, and it is often necessary to supplementary by experiment. So in this slide, I would like to share with you a few ideas about moving fluid. So I hope students need to understand this very well before we go for the equation for the analysis for moving fluid. So number one is streamline. Streamline is an imaginary curve in the fluid across which at a given instant there is no flow. So the simple ideas of streamline is actually the history of one molecule move from one point to another point. So if, for example, we have a few molecules, okay, we could track all the movement here by showing a line in this diagram. So this is the streamline. So we could streamline is imaginary curve, but actually we could calibrate it in experimental works. So for example, if you search about wind tunnel, so about wind tunnel here, so normally we have a car here. So and then we blow a wind from left to right, for example, and then we install a device called a smoke generator. So smoke generator means it's generate smoke. So and then that smoke will flow at the same direction of the flowing fluid. So the wind direction. So and then we could see the line of the smoke. So that line is actually the streamline. So means that's why when car manufacturer want to have a streamlined body of a car, so they will use a wind tunnel to test whether the flow is good or not. So the first one is the streamline. So and then after this, I will introduce you with two terms of flowing fluid. So one is steady flow and the other one is uniform flow. So we go for the steady flow first. Steady flow is one in which the velocity, pressure, and cross-sectional of the stream may vary from point to point, but do not change with time. So this is the keyword for steady flow. So steady flow means you may have different in velocity, pressure, and cross-sectional and so on, but the value of those things cannot change with time. If at a given point conditions do change with time, the flow is described as unsteady flow. So here, please remember we have two types of flow. One is steady flow and another one is uniform flow. But the opposite behavior of steady flow is called unsteady flow. So I hope students could describe this very well because it's normally asked in the test and final exam. So the third one is the uniform flow. Uniform flow occurs if the velocity at a given instant is the same in magnitude and direction at every point in the fluid. So the keyword for uniform flow is about location. So at every point in the fluid. If at the given instant the velocity changes from point to point, the flow is described as non-uniform flow. So means previously we learn about steady and unsteady flow. So the keyword is time. So means that flow is changing or not changing with time is about steady or unsteady flow. And then if we analyze the behavior of fluid in terms of location, so if it is not change, we call it as a uniform flow. But if the flow is keep changing at one location, so we call it as non-uniform flow. So again, this is very important. So I hope you could describe about steady, unsteady, uniform and non-uniform flow in fluid mechanics. So this is the example of that two kind of flow behavior. Please bear in mind that it can be combination like this one. For example, we have steady flow and uniform. So we could have steady flow and non-uniform. We could have unsteady flow and uniform flow, and we could have unsteady flow and non-uniform. So the idea of this one can be described as I show here. So for example, we have a pipe here, and then inside the pipe we have a water flowing from left to the right. So and then at the same point, okay, so we just take two velocity distribution at time 1 and time 2. So means that this remain the same pipe. So and then let's say we have two location in our pipe, so which is location A and location B here. So and then we call this flow as steady flow, because if we look at point A here, the length of the arrow, it shows the velocity on that point will remain the same when time change from time 1 to time 2. Means that after certain time, the velocity at this point is remain the same. So means that it is a steady flow. So and then we call it, this is a uniform flow, because if we stay at one location, we found that all the velocity here is the same. So means that it is uniform flow. So and then for the second one, it is steady. Okay, if we compare A and B here, so the velocity is changed. But if we compare point A at time 1 and point A at time 2 here, we found there is no changes of this velocity profile. So means that the flow is steady flow because it is not changed according to time. However, if we see the velocity in terms of this location, so we found that the bottom velocity is almost 0. So the middle one is the highest one and the top one is equal to 0. So means that it is non-uniform, because uniform means it is same or not at one location. So and then if we compare A and B, okay, it is different here, okay, but for B here, it is larger compared with A, but this velocity is not changed after certain time. So it's still a steady flow. And then we go for the third condition here. So we have A and B. So it is called unsteady flow and uniform. Why? Because if we see the arrow here, so at point A here, at time t1, so the arrow is like this, but after certain time, means at time 2, we found that the arrow is become larger. So means that there is an increment of velocity after a certain time. So means that it is unsteady flow. But if we look at one single location, for example, we look at this point, so we found that all the velocity here is the same. So means that this flow is uniform. And then situation number 4 here, I think you could describe by yourself. So we found that the velocity here and here after certain time, okay, same location but after certain time, so there is an increment of velocity, so it will make this flow is unsteady flow. And if we see from one location here, so we found that the velocity here is keep changing, so it is not constant, so mean it is non-uniform flow. So I hope you could draw this diagram and explain what is steady, unsteady, uniform and non-uniform flow. So number 4 here that you need to understand is about the real fluid and the ideal fluid. Real fluid is a fluid which when it flows past a boundary, the fluid immediately in contact with the boundary will have the same velocity as the boundary. And ideal fluid is a fluid which is assumed to have no viscosity and in which there are no shear stresses. So here, real fluid means if one type of fluid flow inside the pipe, for example, like this one, so this is the wall of pipe. So when it flow inside a pipe like this one, so it is one phenomenon occur. We learn this in viscosity. We call it as no slip condition. So the no slip condition occur here, so means that the molecule will stick very hard on this surface and then the velocity here will equal to 0. So and then next molecule will travel slower like this, but next molecule here will travel a little bit faster and so on and so forth. So and then it managed to create a velocity distribution like this one. So it is depend on the diameter of the pipe. If the diameter is large, so maybe the velocity distribution will become like this. So means that it start from 0, so it's increased to the maximum velocity. After it reach the maximum velocity, so it will constant at the maximum velocity and start to reduce and make equal to 0 at the end here because of no slip condition. So no slip condition means the velocity is 0 at the boundary here. So these two boundary has velocity equal to 0. So if the diameter of pipe is small, so the velocity distribution maybe looks like this, where the middle point here is the maximum velocity. So this is the real fluid, because in real fluid, the phenomenon of no slip condition is occur. So no slip condition occur because of the viscosity effect. So in simulation, for example, it is difficult for us to add the effect of resistance. So sometimes in our calculation, we assume that our fluid is in ideal condition. So in ideal condition, we call it as an ideal fluid, means that it has no viscosity effect. So no viscosity effect means the molecule is not stick on the surface. So the velocity distribution will look like this. So means that molecule at the surface will travel with same velocity of molecule in the middle here, because there are no viscosity effect that could lead or that cause the fluid stick on the surface. And then in fluid mechanics 2 later on, we will learn about the compressible flow. So the compressible flow or the compressible fluid, so the opposite or the pair of the compressible flow is incompressible flow. So or compressible fluid. So compressible fluid is a fluid which its density will change with pressure. So this is the keyword. If the density change from certain point to another point, so it is called compressible fluid. So in this fluid mechanics 2, we will focus on incompressible fluid only. However, one or two example will show the compressible fluid later on. So and then if we look at the refer back to the point number 1, we call it as a streamline previously. So if we analyze the behavior of the streamline, so we could divide the fluid flow pattern into two groups. One is called laminar and another one is called turbulent. So laminar, sometimes known as a streamline flow, occurs when a fluid flows in parallel layer with no disruption between the layers. However, turbulent flow is a flow regime characterized by chaotic, stochastic property changes. So laminar flow means, for example, we have a pipe here, so and then we have 3 molecules of fluid. So laminar means each molecule fluid here will flow on its own path, and it is not cross each other path. So means that it will flow in good manners, and it easy to predict. Means it is easy for us to trace the streamline here, and to predict means sometimes it is easy for us to represent the streamline here with a mathematical equation, because it follows certain rules. However, turbulent means that there is a chaotic. Chaotic means that the streamline here is moved without any rules. So it can cross each other, it can go down, it can go up, and sometimes it will flow in reverse direction. So flow in reverse direction like this one is normally known as vortex. So if you have a vortex, so means it will rotate like this, create a bubble or create a chaotic or unruled or unpredictable behavior of fluid flow. So that is turbulent. So normally in our application, so we will discuss about the turbulent flow, because it is not easy to get a fully laminar flow in pipe especially. So and then, because laminar flow and turbulent flow is not easy to determine, so it means that we cannot track each molecule behavior, because we cannot see the molecule. So there is one scientist who observed this phenomenon named Osborne-Reynolds. From the observation done by Osborne-Reynolds in 1883 in straight pipes of constant diameter, flow can be assumed to be turbulent if the Reynolds number Re exceeds 4000. So here, please remember, there is one method to determine whether our flow is laminar or turbulent. So we call it as Reynolds number. So please remember this Reynolds number. This is the equation of Reynolds number. So it is rho, velocity and diameter divided by mu, which is the rho here is the density of the flowing fluid. V here is the velocity of the flowing fluid, and the d here is the diameter of the pipe. So and then mu here is the dynamic viscosity of the flowing fluid. So this is the way to determine the whether our flow is laminar or turbulent. Reynolds number here didn't have any units. There are no units. So it is just a number. We call it as dimensionless. So dimension means unit. So dimensionless means there are no units for Reynolds number. So and then there is a limit. If you calculate your Reynolds number for certain application, you found that it is exceed 4000. So it means that your flow inside that application is fully turbulent. Okay, so and then if Reynolds number less than 2000, So we call it as fully laminar. Okay, if the Reynolds number is between 2000 and 4000, so we call it as transition region. Transition region or transition flow. So transition flow means it is not, we need to understand that if the flow is laminar, before it could become fully turbulent, so it needs to change step by step. So it means that in a transition region, you may have 10% turbulent, and then 20%, 30%, until 90%. And then after Reynolds number 4000, we assume that it is 100% turbulent in the flow. Yes, V is the velocity. So this is the device to check the Reynolds number established by Reynolds. So let's say we have a water tank here. So and then we connect this water tank with a see-through pipe like this one. And then if we open the valve here, so the water will flow inside this pipe. And then we put a dye here and ink here. So in the beginning, we found that the ink will stay in straight line. Why? This is the laminar effect. So laminar effects means the molecule here will remain on its own path. So means that the ink here in between the molecule will remain on its path. So and then at certain region, so means before it's become 100% turbulent, so there are a few molecules who start to move without any rules, chaotic. So means that, and if this happen, so means that the ink has possibility to travel upside and downside. So it could travel anywhere here. So however, at this region we could still see the color of the ink, the color of the dye. So and then at fully turbulent region here, so we found that we cannot, the dye dispose in water, we cannot see the color because all the molecule of the ink will go all over the fluid. So means that this region is called fully turbulent region. So this is the way to check our means that to check the existence of laminar and turbulent inside a pipe. So and then the calculation or the derivation of the equation of rho Vd over mu. So we will learn in chapter 7, I think, in under Buckingham Pi theory, Buckingham Pi theorem and similarity. So again, I would like to remind you about the Reynolds number here. So Reynolds number is rho Vd over mu. So rho is the density of water in this case. So velocity is the velocity of water moving inside this pipe. And the diameter here is the inner diameter of this pipe. So and then the mu here is the mu dynamic viscosity of fluid here. So which is water in this case.